get that feeling, where you're trying to piece together a puzzle, but you've just got way too many scattered pieces.
Mm-hmm.
You want to see the big picture, really understand how it fits, but without spending, weeks sorting through it all.
Yeah, information overload.
Exactly. And that's what the deep dive is all about. We take these sprawling collections of information and sort of distill them down to the core insights, give you a shortcut to, well, real understanding.
We're basically your guides, you could say, helping you navigate through maybe complex stuff and pinpoint what truly matters.
You can connect the dots.
Right, and build a solid understanding, but efficiently.
And that brings us to you, our listener, the learner. You're someone who's, naturally curious, you want to grasp things thoroughly, but you value your time, right? And you appreciate clarity.
You're looking for those aha moments.
Yeah, without the overwhelm. And that's exactly what we try to deliver.
So today, our mission is to demystify a pretty fundamental area, experimental design and validity. We're working with some detailed lecture notes here, and the goal is really to extract the crucial concepts, give you a clear and hopefully actionable understanding of how researchers try to establish cause and effect.
Right, we're plunging into the world of controlled studies. We want to see what makes them reliable, and just as importantly, what can throw a wrench in the works.
Definitely.
So our source material today, it's mainly lecture notes focusing on these core principles of experimental design. And guiding us through this fascinating landscape, we have our expert.
Happy to be here.
Okay, let's jump right in then. When we talk about an experiment, what exactly are we talking about, and how does experimental design fit in?
Okay, so basically an experiment, according to these notes, it's a research study where the investigator actively changes something, at least one independent variable.
Actively changes it.
Yeah, that deliberate manipulation, that's the key thing. It's what sets experiments apart from studies where researchers just, observe things as they are.
Like looking at age and income, where you can't really change someone's age for the study.
Exactly. You're not manipulating age. In an experiment, you are manipulating something.
Got it. So the researcher is intentionally tweaking something to see what happens. And then experimental design is the plan, the strategy.
Precisely. Experimental design is the overall structure, the blueprint. It dictates how all the variables in your experiment are arranged and managed. It's how you organize the whole thing to effectively test the impact of that variable you're manipulating.
Right. Okay. So experiment is the act of manipulating. The experimental variable is the thing being manipulated. And experimental design is the strategy for how you do it all. Related, but definitely distinct. Now, these notes mention a kind of shorthand, T, X, O, and R. What's that about?
Yes, the notation. It's pretty standard stuff in design. T usually represents the different treatment groups, so you might have several groups getting different interventions.
Okay.
X symbolizes the treatment itself, the independent variable you're manipulating.
Like different teaching methods.
Yeah, perfect example. X could be method A, method B, maybe a control with no new method.
Okay, T is groups. X is what you're doing to them. What's O?
O stands for the outcome, the observation or the measurement you're taking.
Ah, the results.
Kind of, yeah. What you measure, you'll often see it numbered, like O1, O2, indicating when you took the measurement.
Okay, and R?
R stands for random assignment, assigning participants to those different groups randomly. And this is really, really critical.
Why is that?
Well, it's about making sure the groups are as similar as possible right at the start. We'll definitely come back to why that's so important.
Random assignment, got it. So if we were testing, say, 3 types of fertilizer on plant growth, we'd have 3 treatment groups, T, each getting a different fertilizer, X1, X2, X3.
Right.
And then we'd measure the plant height O later.
Exactly.
And if we've randomly assigned 60 little seedlings to the group.
In that case, the independent variable is the fertilizer type, and it has 3 levels.
Levels. Okay, so levels of independent variables, that's just the different versions of your treatment.
Yeah, the different variations or forms it takes. Different dosages, different teaching methods, different fertilizers in your example. Those are the levels.
Makes sense. The notes also talk about subjects versus participants. Is that a big deal?
The source makes a slight distinction. Subjects are specifically where you get the dependent variable data from. So in your plant example, the plants are the subjects.
Because we measure them.
Right. Participants is maybe a broader term. Anyone involved, like the researchers tending the plants, could be participants in the study process. In human research, though, we often just use participants for the people we're getting data from. It's less critical usually.
Okay, interesting nuance. So Subjects are the source of the key measurements. Now, what makes a good experiment? What are the signs of a well-designed one, according to the notes?
Well, there are several key things. First, and this is huge, is adequate experimental control. Yeah, having ways to isolate the effect of your independent variable. And random assignment, like you said, is a major tool for that.
Okay, control is key. What else?
Second, a reasonable number of levels for your independent variable. You need enough variation to see if there's an effect, but not so many that it gets, too complicated or the differences are tiny.
Right. You need enough contrast to see if anything's actually happening. Makes sense.
Then, practical applicability. Is the experiment actually doable? Is it ethical? Can you afford it? Does it reflect the real world enough?
Good point. No point designing something you can't actually run.
Exactly. Also, you need a clear basis for comparison.
Ah, the control groups again?
Yes. Control groups that get no treatment or contrasting groups that get different treatments. You need something to compare your results to. Otherwise, the numbers don't mean much.
Absolutely. Is my new fertilizer better than nothing? Is it better than the old stuff? You need those comparisons.
Precisely.
Oh.
The notes also stress getting adequate, uncontaminated data, meaning a large enough sample size, minimizing errors when you measure things, and using measurement tools, instruments that are relevant and reliable. Consistent. This touches on measurement validity, which is related.
Okay, good data.
And crucially, a well-designed experiment tries really hard to eliminate confounding and irrelevant variables.
Those other factors that could mess things up.
Exactly. That's kind of the fundamental reason for doing experimental research, to isolate the effect of your independent variable from all that other noise.
Okay, create a clean environment, basically.
Sort of, yeah. Then there's representativeness and generalizability. That's often called external validity.
Can the findings apply elsewhere?
That's it. Can you apply your findings to other people, other places, other situations? The notes warn about, super artificial lab studies that might not work in the real world.
Right.
And finally, simpler designs are often better. Parsimonious. Easier to understand what's really going on if you don't make it overly complex.
Keep it focused. Keep it clear. Got it. Okay, let's shift to experimental validity. What's that umbrella term cover?
Experimental validity. It's basically about the overall trustworthiness and accuracy of your results, how much you can believe them.
Okay.
Our source mentions construct validity. That's about whether your measurements actually capture the concepts you think they're capturing. We'll touch on that again later.
Measurement validity, got it.
But the main ones for us now are external validity, the generalizability we just talked about, and internal validity. That's going to be our main focus.
Internal validity, okay.
There's also statistical conclusion validity, which is about, well, are your stats right? Did you use the right test, have enough power, avoid just fishing for results?
Okay, so external generalizability. Internal, did X cause Y, and statistical, are the numbers solid? And we're zeroing in on internal validity. So what's the heart of that?
Internal validity is really about confidence. How confident are you that the changes you saw in your outcome measure, your dependent variable, were actually caused by the thing you manipulated, your independent variable?
And not something else.
Exactly.
Yeah.
Not by some other factor you didn't control. It's about the strength of your causal claim. High internal validity means you can be pretty sure your treatment worked.
That's the goal, right? Knowing what you did actually made the difference. Okay, this leads us nicely into the pitfalls. Threats to experimental validity. What are these dangers lurking around?
So these threats are basically other variables, things you're not studying directly that could also be influencing your outcome.
Yeah.
All these extraneous variables.
Just other stuff floating around.
Yeah. But when one of those extraneous variables does actually affect your outcome, and it's muddying the waters for your independent variable, that's when it becomes a confounding variable, sometimes called a spurious variable.
Ah, okay. So extraneous is potentially problematic, but confounding is problematic. It's actually messing with your results.
You got it. And the whole point of good experimental design is to try and control or eliminate those confounders.
Right.
And the notes lay out the conditions you generally need to meet to say A causes B. First, there has to be a theoretical link, a reason why A might affect B.
Makes sense.
Second, the time order has to be right. A must happen before B.
Can't cause something that already happened.
Nope. And third, you need to rule out alternative explanations, meaning the relationship isn't just because of some third variable, C, that's influencing both A and B.
So logical link, right time order, and no hidden confounders.
That's the ideal. And like we said, good experiments with high internal validity make those causal claims much stronger. The notes use that classic coffee and heart attacks example for correlation versus causation.
Oh, yeah, I know that one. Explain how that fits.
Sure, you might see studies showing a correlation. People who drink lots of coffee also have more heart attacks.
Right.
But correlation just means they happen together.
Mm.
It doesn't automatically mean coffee causes the heart attacks. There could be a confounder, like smoking.
Oh, people who drink lots of coffee might also smoke more.
It's possible, yeah. And smoking definitely increases heart attack risk. So if you don't account for smoking, you can't be sure if it's the coffee or the smoking, or maybe both, that's linked to the heart attacks. The correlation could be spurious, driven by that third factor.
Right. So just because two things go together doesn't mean one causes the other. You need that careful experiment to try and isolate the cause. Okay, let's dive into some specific threats to internal validity mentioned in the notes. First one, the history effect. What's that?
History effect refers to specific external events, things that happen during your experiment but are outside of it that could influence your outcome.
Like world events.
Could be, or just something local. The notes mention, say, a power failure during computer-based training, or maybe a fire alarm goes off during an exam you're using as a measure.
Ah, okay, an unexpected interruption.
Exactly. Something external happens that affects participants, and it might mess up your results, making it hard to see the treatment's real effect.
So an outside event impacts your participants and potentially masks or distorts the treatment effect.
Got it. What about maturation? Sounds like people just changing over time.
That's exactly it. Maturation refers to natural changes within the participants themselves over the course of the study.
Like kids getting older.
Yeah, or participants getting stronger or more skilled naturally, or even just getting tired or bored if the study is long.
Okay.
The challenge is separating those natural changes from any effects of your treatment. If you test a reading program for a year, kids' reading will likely improve anyway, just from school and getting older, right?
Mm-hmm.
So you need a design, usually involving a control group, to see how much of the improvement is because of your program versus just natural maturation.
Right. Is it my great program, or are they just growing up? Key difference. Next.
Regression toward the mean. It sounds statistical.
It is, yeah. It's a bit tricky. But basically, it happens when you select participants based on extreme scores, really high or really low on some initial measure.
Okay, like picking the lowest scores for extra help.
Exactly. If you measure them again later, their scores tend to naturally drift closer to the average for the whole group, just due to statistical probability. That initial extreme score might have been partly due to luck or a bad day.
So they might improve a bit just because their first score was unusually low?
Precisely. Their score regresses towards the average. So if you give that low-scoring group tutoring, some of their improvement on the post-test might just be this statistical regression, not only the effect of the tutoring. You have to be careful not to misinterpret it.
Okay, so sometimes scores just naturally even out a bit. Interesting. What about mortality? Sounds serious.
In research terms, yeah. It refers to participants dropping out of your study over time, not necessarily dying.
Ah, attrition, okay.
Right, attrition. The threat comes when the dropout rate, or the reasons for dropping out, are different between your groups.
Like if the treatment is really hard.
Exactly. Say you're comparing a tough exercise program with an easy one. If way more people drop out of the tough group because it's too hard.
Then the ones left might be the super motivated ones.
Exactly. They might be different from those who stayed in the easy group. So the groups aren't comparable anymore at the end. Any difference you see might be because the kinds of people left in the groups are different, not just because of the exercise program itself. The pattern of loss matters.
So uneven dropout can skew the results because the remaining groups aren't equivalent. Makes sense. Next threat. The testing effect. How can just taking a test mess things up?
Well, the act of taking a pretest can actually influence how people do on the post-test later.
How so?
Several ways. They might remember the questions, or the pretest makes them more aware of what you're studying, so they pay more attention to it between tests. Or they just get better at taking that specific type of test. Practice effect.
Ah, okay. Like the pretest primes them.
Yeah, it can. The notes mention memory effects, carryover effects. It makes it hard to know if the improvement on the post-test is due to your treatment or just because they took the pretest. Researchers sometimes try to use different but equivalent tests, parallel forms, to reduce this.
So the first test itself changes their performance on the second, separate from the treatment. Tricky. Okay, instrumentation. Sounds like the tools again.
It is. Instrumentation threat means there are changes in how the outcome, the dependent variable, is measured during the study.
The measurement itself changes.
Could be. Maybe you use a slightly different questionnaire for the post-test, or maybe the people doing the observations or scoring get tired or apply the criteria differently over time.
Like different examiners giving slightly different instructions.
That's a great example from the notes. If the way you measure changes, how can you be sure any change in scores is due to the treatment and not just the inconsistent measurement? You need reliable, consistent data collection.
Right. If your measuring stick keeps changing length, your measurements are off. Got it. Last one here, selection bias. We talked about random assignment helping with this.
Exactly. Selection bias happens when the groups you're comparing weren't equivalent to begin with, right at the start.
How does that happen?
If you don't use random assignment, maybe people choose which group they want to be in, or the researcher uses existing groups, like different classrooms, that might already be different in important ways.
Like one class is the advanced class.
Perfect example from the notes. If you compare an advanced class to a regular class, after giving one of them a new teaching method, how do you know the difference in scores isn't just because one class was already higher achieving?
Right.
So random assignment is key. It aims to make the groups equivalent, on average, before the treatment starts. It levels the playing field and helps control for all those potential pre-existing differences, those confounders. That gives you much higher internal validity.
Okay, so random assignment is really fundamental for tackling selection bias and making causal claims stronger. Whew, that's a lot of potential pitfalls. Now, the notes briefly list some types of experimental designs. Can you give us a quick tour?
Sure. A really basic one is the post-test only control group design. Randomly assign people to treatment or control, do the treatment, then measure everyone once at the end.
Simple but
But you don't know if the groups were really the same at the start on your outcome measure because you didn't measure them beforehand. No baseline.
right. So what fixes
The
that?
pre-test, post-test control group design. Same random assignment to treatment or control, but you measure everyone before the treatment, pre-test, and after post-test.
So you get the baseline, you can see the change.
Exactly.
Yeah.
Pro is you can check starting equivalence and measure change.
Mm.
Con is, well, that pretest might cause testing effects, like we discussed. And it costs more, takes more time.
Trade-offs.
Okay, what else? There's a fancy one called the Solomon 4 group design. It combines the first two to try and figure out if the pretest is having an effect. It's more complex, uses 4 groups.
Sounds complicated.
It is, but powerful if you really need to isolate that testing effect. Then you have factorial designs.
Factorial.
That's when you want to look at 2 or more independent variables at the same time, like maybe type of therapy and duration of therapy. And you can also see if they interact. Maybe one therapy works best only if it's long duration.
Okay, looking at multiple factors.
Right. And you can even combine manipulated variables with ones you can't manipulate, like treatment type and gender, in these designs. Finally, repeated measures designs.
Measuring the same people multiple times.
Yeah, over time. Useful to see if a treatment effect lasts or how things change gradually. But you have higher risks of dropouts, mortality, practice effects from repeated testing, and you might need different but equal tests each time.
So a whole range of designs, each with pros and cons depending on your question and what threats you're worried about. Makes sense. Lastly, the notes mention interpreting results. What's the basic idea there?
Well, fundamentally, you're usually comparing the average scores between your groups.
Comparing the averages?
Yeah. Did the treatment group improve more from pretest to post-test than the control group? Is the treatment group's average score significantly higher on the post-test than the control group's? If you had multiple treatments, which one ended up with the best average score?
So you look at the numbers, the group averages, and see if the differences line up with what you expected your manipulation to do.
Pretty much. You're seeing if the data supports your hypothesis about the cause and effect relationship.
Well, this has definitely been a deep dive. We've really unpacked the core ideas of experimental design and validity.
Yeah, we've covered a lot. Defining experiments, the notation, what makes a good design, those crucial threats to internal validity especially, and then a quick look at different design types and interpreting results.
And for you, our listener, the learner, we hope this gives you a solid framework, a way to understand how researchers try to figure out cause and effect, and maybe some tools to critically look at research claims you come across.
Absolutely. Think about it next time you hear someone claim, doing X causes Y. Maybe pause and think.
Yeah.
Think about the concepts we discussed. Could there be confounding variables?
Mm-hmm.
Were the groups they're comparing really equivalent to start with? Was it even an experiment? Or just a correlation? Could history or maturation play a role?
Really good questions to ask. Puts those claims in perspective.
Helps you evaluate the evidence.
Well, thanks thanks for joining us on this exploration. We really hope it shed light on experimental design. We'll definitely revisit related topics, maybe dig into construct validity next time or specific methodologies.
Sounds good.
Until our next deep dive, keep thinking critically.